Welcome back to ECE 220. We begin today, once we start getting into the course material, with Chapter 8. We have one more chapter after that, Chapter 9, which is sinusoidal steady state analysis. But we need to get to steady state, and before we get there, we have to go through Chapter 8, which is the transient behavior of more than just first-order circuits. Chapter 8 will be dealing with second-order circuits, and if you've been reading ahead, you know what we'll be talking about today. Today, your lab report, if you're in Group A, your lab report for number 3 is due. We will have a break in some of our class meeting times. This Friday we will not be in class. But next Friday, here's the rub. If you have lab, please go to lab next Friday. We won't have class next Friday, but you'll still have your lab. So if you're in the Friday lab section of Group A, that's why I'm circling it here. I'm not dismissing the lab component. You have to still do that, but the class next Friday are definitely not happening in this classroom. Group A, your pre-lab for lab number 4, and we only have 5 labs, not 5 more labs. We only have 5 total labs, so we're getting close to being finished with our labs. Lab number 4, pre-lab, is due on Saturday of this week. Exam number 3, review session, will be Monday of next week, which is the week of our third exam. Exam number 3 is on Thursday of next week, which is a week from tomorrow, and that will be covering material that you just finished homework on last night. Homeworks 7, 8, and 9 will be the content material for exam number 3. Group B, the night before the exam, maybe you'll finish it up. I'm giving you a day off Friday, so if you're in Group B, you can write up your lab number 3 report since you completed that lab yesterday. You will then need to turn that in next Wednesday, the day before our exam, exam number 3. If you can keep all of this straight, good luck. I'm struggling, but you have it down. You now have reached steady state, and today we're going to experience some more transients. We're going to be in Chapter 8, which is RLC circuits, and this class we will focus on 2 particular structures of RLC circuits. Now we're putting all 3 of these circuit elements that we've been playing with all semester together, either in a parallel combination or a series combination. That's what we will focus on in class in Chapter 8. And I think you know that it might be possible that we can have more than just 3 elements, but after you effectively combine them, you now have 3 elements in either parallel or series, and we will introduce sources so that we can have step response behavior relative to these types of circuits. Then we'll look at limiting cases of these parallel and series circuits, and really we're asking the question, can we make these 2 circuits look the same, or these 2 structures? Can that be possible? Well, I wouldn't be asking that question probably if it was not. So that will lead us into, and I'm not going to spoil it quite yet with just the preview, but we'll get a tank circuit that results. When those 2 circuits look the same, we'll investigate the dynamics of this tank circuit, and then we'll go back to the full scale RLC circuit parallel and look at its dynamics. And then we'll talk about the different dynamical behavior. I'm going to give this away, I know, but I'm trying not to give you too many spoilers. I'm wanting to say more, but I can't. I'm trying to bite my tongue. But we will now figure out what kind of dynamics exist or are possible with RLC circuits. And that all depends, obviously, on the values of the resistor, inductor, and capacitor. Here are the two circuits that we will focus on in this class. And I should point out, not sure what color my pen is, but the arrangement of these, although I've sort of drawn them in RLC, RLC from left to right, that arrangement doesn't really matter. We could have a CLR. I think that's a cleaner, isn't it? We'll stay away. But anyway, the arrangement of these, I'm not supposed to do product placement in these classes, so I'll try to avoid that. So we have an RLC series or parallel circuit. The arrangement or order of these doesn't matter. What I mean by that is you could interchange the resistor and inductor's location, and you're still going to get the same dynamical behavior. You would have the same current going through this circuit as you do the other. You can interchange those locations of your circuit elements. That's not critical. You could shuffle the R's and the L's and the C's. As long as you have those three in parallel, you're going to have the same dynamical behavior, as long as you preserve the same values. If you change values, then you have different dynamical behavior, but it will be the same no matter how you shuffle their location. Is that clear? So if the book gives you a problem with a different orientation or arrangement, you can't throw up your hands, or on the exam you can't say, well, we've never seen that one. The exam gave us an LRC circuit. We've never done that one. Yes, you have. Okay? So RLC, LRC, CLR, whatever, it's the same. Now we want to ask, is it possible to make these two series and parallel circuits look the same? Can we make them to be equivalent? Is it possible to make one transform into the other? Can we make one into the other and vice versa? Can we turn this parallel circuit into a parallel circuit, or a series circuit into a series circuit? What? All right, let's put on our morphing headgear, whatever, virtual reality headpiece. Augmented reality maybe is even better. Now we can put something augmented on there. What if we said, oh, let's let R in this circuit go to infinity? What does that do for us? If we let R go to infinity in the parallel circuit, what does the resulting circuit look like? What happens to R when it gets really, 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 really big on the left? It opens up, doesn't it? It becomes an infinite impedance. Our circuit now looks like that. Can we make the right side look like that? The series circuit. Well, we can if we go in the other way, in the other limit. What if R goes to 0? On the right, in the series configuration, what happens now? What does that circuit become as R goes to 0? Now we short that wire, or the resistor, and now we have this, if I keep the orientation, but you have your morphing headwear eyepiece on. You can now contract and expand the wires appropriate to make the right side look just like the left side. We okay with that? So now when we say let's let the resistance go away or reduce our damping, it's going to depend on which circuit we start with. If we start with a parallel, making the resistance go away says, oh, we need to really increase the resistance value to make it go away. If we want the resistance, if we want the damping, the resistance to go away on the right, we send R to 0. So you have to kind of keep these two extremes, these limiting cases, sort of in the same thought process, but they're completely different limits. But they yield the same thing. And we're dealing with two different limits because we're starting with two different structures, a parallel structure or a series structure. So keep me honest. If I say let the damping go to 0, it's going to need to mean two different things as far as the particular way that R moves. Does it go to infinity or does it go to 0? And it depends on whether we're starting with parallel or series. We clear on that? So when somebody says, oh, we're letting the damping go to 0, you have to kind of know where did you start in terms of if you were in the lab and they say, oh, remove the damping, remove the energy dissipation in that circuit as best you can. You now want to get rid of the resistor. Well, in one case you pull it, and the other you replace it with a wire. All right. Those two circuits now should seem the same, and we're going to call that a tank circuit. And I'm going to draw it usually in this configuration. So now we have this tank circuit, and let's just label it. Here's an L, or maybe I want to put, I don't know, let's say L there and C there. And what else? Well, we have the same voltage across those, and they share the same current. Those two circuit elements now have a lot in common in terms of variables that describe their dynamical behavior. They share the same voltage and they share the same current. So now we're asking, how does the tank circuit behave? Is it well behaved? Is it ornery? It's actually a little bit ornery. Need to liven things up a little bit in this class, huh? We've been dealing with resistive circuits, which just duplicate whatever you excite them with. We have opened it up a little bit with first order, one energy storage device. Now we have exponentials, and last time, what did we learn about exponentials? They can go both ways, right? They can be exponentially decaying or they can be exponentially expanding, depending on the damping characteristics of your circuit. So can we describe the dynamic behavior of this tank circuit? Well, everybody likes to do mesh, so let's just do mesh. Let's do a KVL analysis on this tank circuit. Now you have all sorts of machinery, all sorts of skills to employ in analyzing these circuits. Let's do KVL. And let's start in the lower left, being consistent. The voltage dropped from bottom to top on that inductor using the I that I've labeled, the reference current. It's L di dt. Oh, and what variables usually should we be focusing on? I'm all over the map. I want to just run, and I can't. I'm having to rein back. Sorry, all these terms. What variables should we focus on if we're trying to write dynamical behavior of circuit elements that contain inductors and capacitors? Does it really matter? Which ones should we probably worry more about? Is it really? What state are we in? Arizona? We want to keep track of the state of this circuit. State variables. We know what the state variables are for an inductor and a capacitor. So let's focus on, let's use state variables as best we can when we're starting to write differential equations for these circuits, or use state variables to describe the dynamics or write the dynamics of these circuits. KVL. So now we said we had L di dt. That was the voltage drop from bottom to top. Well, now if we're using state variables, let's just say plus the voltage dropped across that capacitor. That's our state variable. Plus, oh, no, not now. Neither one. Couldn't get anything to work last night. Now everything wants to work. Plus V. Are we okay with that? Why are we using V? What? So now what happens if we said C dV dt? Is that what you're asking? So now we could write C dV dt. You're getting ahead of me. We now have one equation in two variables, and we probably want just one first order differential equation in terms of one dependent variable, I or V. So we're going to have to sort this out, but we said we want to keep track of the current in the inductor, that's the I, and the voltage of the capacitor, that's the V. So this is now giving us this dynamic relationship. It'd be nice now if we could connect I and V and remove one of those. Can we eliminate I or V? Can we write one in terms of the other? And you're saying, well, why didn't we use ice? It's getting cold. It's getting that time of the year. So why not focus on ice, which is I is equal to C dV dt. What if we replace I with that? So then we'll end up with one equation in terms of one variable V. Or now we say L is d by dt of C dV dt. Is that okay? Is that kind of ugly, but you know what I'm doing? We had L di dt, and we're replacing I with C dV dt, plus V is equal to 0. We're assuming our inductors and capacitors are time invariant. They're not changing with time. They're constant. So if you want to sound kind of ECE and somebody says, oh, L and C are constant, you say, oh, they're time invariant? Yeah. we can use the language, okay? So now we have time invariant L's and C's. The C goes outside the derivatives, and we now have LC, the second derivative of v dt, plus v is equal to 0. And now we have a governing differential equation. We have a second order differential equation that describes the behavior of, in this case, the voltage in that tank circuit. This is the LC parallel circuit, or you might want to isolate the derivative. Question? Oh, I was afraid that was going to be asked. So the question was, why is the voltage in my labeling? Come on, Tharp, what are you doing? So I was hoping you had this morphing headset on and you were okay with me just kind of throwing things around. You caught it. But we had V going from bottom to top, didn't we? So I should have said V sub L is the negative of this V. But if you just say, well, let me just say, if the voltage, if I took out your voltmeter and put the positive lead up top and the negative lead, I'm going to see the same voltage dropped across L and C in that sense, right? So that's the loose sense that I'm describing. Then when we wrote our KVL equation, the voltage dropped. I didn't say that was V. The voltage dropped across the inductor is L di dt using the I that I've had there. So now the voltage here, I think this is your question, V sub L is that way, and V sub L we were using is that. So we just replaced V sub L. I didn't even show it, but I just said, oh, V sub L in terms of I is L di dt. Is that okay? So I kind of, well, I want you to be thinking about this, but I kind of didn't want you to be thinking about it. But are we clear now on that? So I don't want you to be confused. The voltage dropped, pardon? Are we never going to have what? Negative? Well, you could, depending on, so the question was, are we ever going to have negative L di dt? It depends on the reference of your current, how you've defined your current, and how you want to label your circuit. But typically, if we do the passive sign convention, PSC, is that what we were saying most of the early part of the semester? Then you can just draw your inductor, label it accordingly with the plus minus and the current going into the plus terminal. But if you haven't done that, you might end up saying, oh, relative to the way I've defined my current, this L di dt I have to say is a minus. It's just going to depend on how you've drawn or labeled your circuit. But everybody's answers better come out the same in terms of the same general behavior. If I define my I just the opposite of yours, I'm going to get a negative answer, but will be consistent. So we should get consistent results. Where I was going with this, I think, before somebody asked about the sign on the voltage of the inductor, which was fine, that's a valid question, is I wanted to isolate my second derivative by itself. I want to just keep that on the left. Maybe that's the standard form, and it will be when you start going to higher classes and you start learning about state variable descriptions in 320 maybe, 340. But now let's write this as the second derivative of V with respect to time is equal to minus 1 over LC V. So you might see it this way. And those are consistent. And we have now a second order differential equation. We had two energy storage devices, or energy storage elements, in the form of L and C. Generically, if you had three energy storage elements, you would expect a third order differential equation. Generically, I'm saying they wouldn't combine into an effective capacitor. Two of those capacitors might lump into one. I'm saying generically that wouldn't happen. And now if you had two inductors and one capacitor, you would be expecting a third order circuit. If you had 5 energy storage devices or elements, generically you would be expecting a fifth order circuit. What you can take away from today is what you're learning about second order a lot of times generalizes to much higher order systems. Somebody might have a 10th order system and you look at its step response and you go, that looks like a second order system. They start a lot of circuits or a lot of systems generalized to looking like second order systems. So what you're learning today in chapter 8 is very useful. Don't go home and say, yeah, but we just learned second order. What if I have a fourth order? Well, a lot of times you can approximate a fourth order with a second order. And you now know how to solve second orders, or you will by the end of this chapter. Can we anticipate what the time functional expression for V looks like? We now know the second derivative of V is equal to basically V, the same structure. What in your background have you run across that if you differentiate it twice, you get the same functional form back? E? You're both right. Somebody said E, somebody said sinusoids. If we put a complex exponential on that E, we'll get sinusoids. So today we're focusing on sinusoids because we have a second order derivative. You differentiate a cosine twice, you get that second order back, right? So suppose V sub c of t was actually some cosine omega t. Now we're just reviewing our calculus. The first derivative of that, what's the derivative of a cosine? Negative sine. And do we need to worry about the omega in the argument? Yeah, we have to differentiate that. So we now have negative sine omega t, derivative of omega t with respect to time gives us the omega, or this now is minus omega sine omega t. What's the second derivative? That's just the first derivative of what we just found, omega sine omega t. And the derivative of sine is cosine. But you still have to differentiate the argument again, so we get another omega. We now have omega squared. We have minus omega squared cosine omega t. And if we compared these two expressions, wow, we recovered the minus sign on the right-hand side. Now they'll be the same if we simply say, well, that omega squared is 1 over LC. Right? So now the second derivative of cosine is minus omega squared cosine omega t. Well, that's cosine omega t with minus 1 over LC equal to minus omega squared. Or omega squared is 1 over LC. we now know what the frequency is based on the parameter values of L and C, knowing our calculus. So now this comparing equations now allows us to say that omega squared is 1 over LC. And we actually give that, well, the square root of that, the positive square root of that, we give that its own name. We say that's the resonant frequency. This tank circuit has a resonant frequency given by 1 over the square root of LC. So omega naught and we use that all the time. When we tune our radio, we actually have this tank circuit, and it likes to oscillate at specific frequencies. In the old days, you'd tear a radio apart and you'd see this big capacitor in there, these plates moving, and you're adjusting that as you adjust the dial. You're tuning this resonant tank circuit, and when it gets to the right frequency, you get your radio signal that you want. Good use of a tank. Does this structure for V sub C seem reasonable? Now we say that this circuit, this tank circuit, this LC circuit, the voltage across that capacitor behaves like a sinusoid, a cosine. Does that make sense? We have two energy storage devices, and they're kind of just playing catch, aren't they, with their energy. One stores up energy in the electric field, and then it says, oh, you want it? I'll give it to you. And then it gives it over to the magnetic field, and it just oscillates back and forth. Don't go to sleep on me. I'm rocking you to sleep. That's what I was meaning by. With the natural frequency, you have a natural frequency, but we're usually higher than that, aren't we, with electrical? Much higher, but this structure does seem reasonable. We have two energy storage devices. Or elements. That in fact pass energy back and forth. And what else? Well, we don't have a resistor in that tank, so there's no dissipation of energy. That last implication is making an assumption. What's the assumption? Ideal. We're assuming these inductors and capacitors are ideal. We know in reality they have some internal resistance. So you put that tank circuit together, eventually it's going to lose all of its energy just because of the natural resistance in the coil and the capacitor. But ideal, they just keep sharing that, or exchanging energy back and forth. Yes. So now, do the current and the voltage behave similarly, I think was the question. And the answer is yes. So they both behave, or they both are governed by this second order differential equation. So you now know that anything in this circuit has that same that resonant frequency. And it then will oscillate sinusoidally, current or voltage. Can we compare this behavior with a mechanical system? Any mechanical engineers in the room? You're afraid to identify yourself, huh? I applaud the bravery of someone actually identifying that discipline in a room full of mostly ECE. Hey, we're all engineers, right? And what you will learn is that we all sort of study similar systems, and you can think in electrical ways or mechanical ways. You can even start thinking in both ways. Here's a mass spring system. There's no damping. This is ideal. We don't have any dissipation of energy. This is no damping. Am I making you nervous now? Now we're back in physics. Physics 141, is that where this came? You can see this again in subsequent classes, even outside of mechanical engineering. We talk about this in 441 all the time. We have it in the lab. Just across the hall from 220, there's a mass spring damper system. This one doesn't have a dash pot or a damper. What's the dynamic behavior of this? Oh, let me tell you what my variable of interest is the position and velocity of that mass. That's the x and the x prime. So I now know the acceleration of that mass times mass plus the energy in the spring is equal to 0. And now we can solve that for the second derivative of the position, or we can solve it for the acceleration, and this is now minus k over mx. And I think it's pretty easy to think about what happens if you had a spring and a mass, and you pulled that spring, gave it some potential energy, and released it, and there's no damping. That's just going to keep shaking, isn't it? Well, that's what's happening with the energy in this tank circuit. And before class I said, what's the origin? I asked Google. I said, what's the origin of tank circuit? That's kind of what I thought. The sloshing back and forth in a tank, water sloshing back and forth. The energy in this inductor and capacitor are just tossing this energy back and forth, or passing the energy back and forth. As is this spring, it's just converting from potential to kinetic, potential to kinetic, and it just keeps doing that as long as there's no damping. So when you see this tank circuit, you could think this way as well. You could say, oh, a mass spring system. That's kind of the thought process you want to be thinking about. Now, let's put in some damping. Let's describe this now more generally. We've now moved from the tank to an RLC circuit, and we want to now model this system's behavior or find its dynamics. And what variables do we want to focus on? Okay, you could give me the generic answer and say state variables, and then you don't have to remember which one's which for the inductor and capacitor. And I'd have to kind of say, okay, that's correct, but now be more specific. What are the state variables in this circuit? Is it the resistor's current? Is that a state variable? No. What about the inductor's current? Yeah, that one's okay. What about the capacitor's current? That doesn't stay continuous, does it? That can change instantaneously. If we're interested in parameters relative to the capacitor, we may want to focus on its voltage. So let's now say that we have the capacitor voltage, and now let's write a KCL. We did a KVL before, let's write a KCL in terms of these state variables if we can. So now we know the voltage dropped across all three is the same. We now know the current in the resistor is V sub C over R. The current in the inductor, we're going to just leave as the current in the inductor. That's a state variable. And then we'll figure out, can we get rid of some of these? And then we have KCL. The current in the capacitor is ice. That's now C dV sub C dt, and that's equal to 0. We okay there. Now we have one equation, but it includes a couple different variables. We want to write it in terms of just one. So now we start going through Eli the Iceman. We say, okay, we have Eli. That says that V sub L is equal to L di sub L dt. Or we have ice, which is I sub C is equal to C dV sub C dt. Do you see how we could maybe pick one of those, Eli or ice, to help us write this expression in terms of just one variable instead of both I sub L and V sub C? It really just needs us to be reminded that the voltage dropped across both of those is the same. So V sub C is the same as V sub L. Now wherever we see V sub C, we can write it in terms of the first derivative of I sub L with a scaling factor of L. Or now we have V sub C, which we're going to replace with L di dt, over R, plus I sub L plus C, and now we need to differentiate V sub C, but that's just L di sub L dt. Or just rearranging these, we now have LC times the second derivative of I sub L with respect to time plus L over R di sub L dt plus I sub L is equal to 0. And now we have a second order differential equation in terms of I sub L. We now know how I sub L varies with respect to time, the inductor current. And if we need the capacitor voltage, we just find the first derivative of the inductor current and multiply by L, and now we have the capacitor's voltage if we need to back that variable out. Well, we can clean this up or make this look more like what's in the textbook if we simply multiply everything, both sides, by 1 over LC, which now gives us the second derivative of I sub L with respect to time plus 1 over RC di sub L dt plus 1 over LC I sub L. And there's that 1 over LC. That was the resonant frequency squared. So now we have different things floating around that we are comfortable with. RC we've seen before. These are just parameters in this second order differential equation. Do we anticipate a structure for I sub L, what it might look like? Now we go back to the more general and we say, well, let's look at it as an exponential, where that exponential could be a complex variable. So now let's just go ahead and assume, or let, I sub L of t be a e to the st. Let's just assume that structure, and we now need to figure out eventually what these variables are. A and s are yet to be determined values. Right now they're unknown. But we want to find those, and if we want to find those, then this I sub L, so with A and S unknown variables, let me finish that, variables to find or determine. So if we use that structure in this second order differential equation, now we can, let's just find some of these expressions. We have I sub L is a e to the st. What's the first derivative of I sub L? The s just pops out in front. We have as e to the st, and the second derivative, we just continue with that process, and we now have as squared e to the st. If we now put those in where they belong into this differential equation that governs the natural behavior of this parallel RLC circuit, we end up with a s squared e to the st, that's the second derivative of I sub L with respect to time, plus 1 over RC times the first derivative, plus 1 over LC times I sub L. There's a common factor in all three of those terms, and it's a e to the st. We factor that out, and we're left with s squared plus 1 over RCS plus 1 over LC, and that's equal to 0. We're assuming a non-trivial solution. You could say, oh, I sub L is equal to 0. That's a solution to your second order difference. Yes, it is, but it's trivial. We want a non-trivial. We're assuming a e to the st is non-zero. We can divide that out, and now we know what s needs to satisfy. The bracketed term needs to equal 0 for us to have a non-trivial solution. S needs to now satisfy that second order expression in S, or that quadratic polynomial. For a non-trivial solution to this parallel RLC circuit, we need a e to the st to not equal to 0. And that now allows us to say that whatever was in the brackets, therefore s squared plus 1 over RCS plus 1 over LC is equal to 0. And that looked like an L up top. It shouldn't be. That's now 1 over RC. This is, in fact, equation 3 in the textbook, and this is referred to as the characteristic equation. This gives you the characteristic behavior of your circuit if you find the values of S that satisfy this quadratic equation. This is now the quadratic or characteristic equation for the parallel RLC circuit. And we need to now find values of S that satisfy that. How do we do that? It's quadratic. We use the quadratic formula. What did you find for possible values of S if they were generically associated with this quadratic equation? What kinds of S's could you end up with? Real, complex, purely imaginary. It all depends on R, L, and C. That's where we will begin, is figuring out what the structure of these solutions look like when we have these different types of solutions to this quadratic equation. When S is purely real, when it's complex, and when it's purely imaginary. We'll pick up there next time.